Hi, this is the second video in the System Design Building Block series. If you missed previous video, there will be a link to the playlist somewhere here, and I will also add it to the description. In this series, we are discussing different front-end topics that will help you to ace system design interview, even if you have never seen before the application that you need to design. Today, we are going to talk about web storages. We will discuss local storages, session storages, indexeddb, and others. We will also discuss when it's better to move data to the server and do not use client-side storages at all. Let's get started.
The first question is, what are storages and when do we need them? Storage is a place where we store data. The simplest storage is a JavaScript memory where we can store the values of variables. When do we need storage? We need it in any application where there is a need to store data. Data storage is not needed for simple static sites, which sometimes don't even require JavaScript, as there are just simple HTML pages. The next question is, what is the problem we are trying to solve in this video? I've noticed that it is not always easy for developers to choose the right place for storing data. Some storages are overused, while others remains in the shadows. For example, local storage is often used as the default storage, while storages such as session storage and indexeddb are relatively less popular. This video will help to understand which tool is best suited for a particular case. Which storages will we discuss? We'll discuss URL, cookies, session storage, local storage, cache API, indexeddb, and remote databases. What will we leave out of the scope? We will not discuss the file system API because it has very poor browser support. And we will also skip WebSQL because it is now deprecated and replaced by indexeddb. Before we begin, it's important to understand what an origin is because we will refer to this term often during this video. An origin is a combination of protocol, hostname, and port. Protocol might be HTTP or HTTPS. Hostname is the address of the site. Port is a port on the server to which we address to receive a website. The port is usually hidden because we use the default port. Also, please look at an example. Example.com and example.com/app/index.html have the same origins. That's all, and we are ready to start. Let's start with a URL. Considering a URL as a storage is not obvious. The URL has search parameters or a query string. We usually think of it as a query parameters, however we can also use it as storage. URL search parameters will survive a page refresh, but will be lost when the page is closed. Therefore, we cannot consider URL search parameters as a safe place to store data. So, when may search parameters be useful? They have one unique feature. They are easy to share with other users and can be saved in your browser bookmarks. Other storages don't have this feature. For example, we can't easily save the page state in local storage and share it with other users later. URL search parameters are easy to use. They allow for easy data sharing between users and saving the page state in bookmarks. However, they are not good as storage because they are fragile, they can be easily removed or lost, they are not very secure, all data is visible, and they have small capacity. For example, in Microsoft Edge, it can include only 2000 symbols. It is suitable mainly for short and primitive data like string, number, or Boolean values. Where might using URL search parameters be useful? For example, for current page state. It's ideal for applications where you want to share the state, such as configured view on a dashboard or map. And for navigation state. URL search parameters are a good place for storing navigation state, like the page number, filter, and search query. For example, in a table component, you usually have many configured parameters, like filters and sorting. Or in an online clothes shop, when a user wants to share a page with a friend to ask for help in choosing something. We should also use URL search parameters in such cases. The next storage is cookies. I'm sure that you have all heard about cookies. At least you have all accepted them many times. Or maybe not. Cookies are distinct from other storages. They have multiple unique features. The two main are cookies can be set by the server and cookies will be automatically sent to the server. Cookies are widely supported and easy to use. They provide better protection against cross-site scripting attacks because we can use the HTTP-only parameter to hide cookies from attackers if they gain access to the code. However, cookies have limited storage capacity, about 4 KB per origin, and they will be sent with every HTTP request, increasing HTTP overhead. Based on these issues, we can't consider cookies as a complete storage solution for data. However, cookies can be very useful in a limited number of scenarios. Let's look at them. Cookies are useful for session management, personalization, and tracking user behavior. Let's look at each scenario. We know that cookies can be set by the server and they are automatically sent with each request. These two features make cookies an ideal tool for managing user sessions. This process does not require JavaScript to manage the sending of session information. Let's see how it works. The user fills in credentials, login and password, and the browser sends them to the server. The server validates them and, if correct, sends a successful response to the browser with a token in cookies. For subsequent requests, the browser automatically sends cookies with a request. The server validates the token from the cookies, and if it's valid, the server recognizes the user as authorized and returns a response. The next topic is personalization. Since cookies are sent with each request, we can display a personalized page on the server when the browser requests the page for the first time. Let's look how it works. First visit. The user visits the site, selects language and other settings. The browser sends the settings to the server. The server sets cookies for the browser. Next visit. The browser sends a request to the page. Cookies are sent automatically. The server reads the cookies and returns a personalized page. Notice how we don't need to request the page in the default language, determine the user's language, and then request the page in the correct language. If cookies are set, we request the page in the correct language with the first request. The next use of cookies is tracking users' behavior. Let's consider an example. Site A displays advertisement provided by an advertising provider. A user visits this site. The advertisement script sends user information to the advertisement provider server. We assume that the advertisement was added to the site via JavaScript or an iframe. The advertisement provider server, upon receiving user information, generates a unique user ID based on the sent information. The provider server sets cookies with the user ID in the user's browser. The browser saves cookies for the advertisement provider server address. Later, the user visits another site that connects to the same provider. When the advertisement script requests an advertisement, it also sends cookies with the user ID to the provider server. Provider server uses the user ID to look up the information about the user, such as previously visited sites, to show personalized advertisements. We finally reached the first candidate that we can really use for storing data. After all, cookies and URL search parameters have dedicated purposes and are not usually used for storing data. Local storage is persistent storage. Persistence means that data will not be deleted after a certain time as long as we respect quotas and don't exceed them, which we'll discuss later. And it's easy to use. Local storage is simple. It's not very powerful and therefore it's really easy to start using it. However, it has some drawbacks. Limited capacity. Typically, browsers provide 5 MB per origin, but in some cases, like in WebKit-based browsers, this may only be 2.5 MB because JavaScript stores strings in UTF-16 format. It has slow synchronous API. Local storage operations are not asynchronous. This means that local storage operations will occupy the main thread, which can slow down the application. It is not available inside web or service workers. Due to its synchronous API, which must be executed in the main thread, it is not available there. This is important for storage because one of the reasons to use web storages is for offline features. Service workers are a core tool in providing offline mode, so it can be inconvenient that local storage can be used inside a service worker. And it supports only strings. Although local storage is easy to use, it offers a fairly primitive feature set. It does not support data types other than strings, meaning a developer will need to encode-decode data each time they want to read or write it. Such processes require additional resources and may slow down the application. Let's consider cases where local storage may be useful. The first one is persistent client storage. We'll discuss later that local storage is not completely persistent and data can still get lost, which is why local storage should not be used for important data. But in some cases, the suggested persistence is sufficient. We can locally store various user settings and applications data, such as selected them, language, and other settings. This is useful when we can't or don't want to use a database. The next case is offline usage. Where we need offline mode, local storage is the easiest solution for storing data. For example, when a user is offline, they perform some operations. We can save the results of these operations in local storage and send them to the server later. With local storage, we can develop a simple offline-first application or an application that stores some data on the client side. For instance, we can use local storage for creating a simple to-do list. It may be used offline only, or if we have a backend, we can use local storage as a temporary storage for periods when the user doesn't have an internet connection. Another possible case is saving drafts. Drafts are common in applications that involve lengthy user input, such as blogging platforms like Medium, where users can edit a single text or form for a long period of time. Should we avoid local storage in most cases? Local storage is often criticized for its small capacity and slow performance. There is a common belief that other storage options like indexeddb are always better. However, I disagree with it. Local storage can be quite effective in certain scenarios, especially when dealing with small amounts of data. In the real world, many applications continue to use local storage because it's simple and convenient. It's crucial to understand that while local storage isn't scalable, it can be a suitable choice for storing limited data amounts. Before diving into session storage, let's clarify what a session means. A session begins when a user opens a web page in a browser. Session storage retains data during tab refreshes and restores, even if the browser is closed, as long as we're within the same session. A session ends and its session storage is cleared when the user closes a tab or when it's closed by the browser and not restored. 2 more points. Session storage does not transfer data between tabs, even if they have the same origin. One tab is one session. The exception to the previous rule is that if a tab has been duplicated, the original tab and the duplicated tab will share the same session store. The advantages of session storage is similar to local storage, but with 2 notable distinctions. It automatically clears data at the end of the session, eliminating the need for manual data deletion. Some browsers, like Internet Explorer for example, offer more space for session storage than local storage, and it operates under a separate quota system. Also, session storage shares the same drawbacks with local storage. Let's look on practical uses of session storage. The first one is caching. Store data retrieving from the server once and reuse it throughout the session. Automatic cleanup of session storage helps manage cache effectively. Data sharing across screens. It's ideal for transferring user or system data across different screens within the same session, particularly useful for multi-step processes, like wizards, for example. And it's also useful for storing global configuration. It's a good alternative to global variables or storage managers for keeping global application settings. The next option is Cache API. Cache API, distinct from browser cache, is dedicated for storing request responses pairs. It is accessible in web and service workers, making it a unique storage option. Here how it works. A client requests an HTML page. Service worker intercepts the request. The request was not found in the cache, so the service worker requests the page from the server. Upon receiving the HTML page, service worker stores it in the cache. Lately, the client requests the same HTML page again. Request for the page is intercepted by service worker. Request is found in the cache. Therefore, it would be returned to the client without request to the server. Unlike local or session storage, Cache API is not for general storage, but specifically for storing server responses. Let's look on use cases. The Cache API in combination with service workers plays a crucial role in enabling offline mode for web applications. By caching assets such as HTML, CSS, and other static files, applications can function without a network connection. Even if offline mode isn't a requirement, the Cache API still offers significant benefits. It reduces network requests by reusing cached assets, leading to faster page load times since static files are retrieved from disk rather than being requested from the server each time. An example of using Cache API in real life is Slack. Service workers and cache are used in Slack for efficient app loading and offline functionality. By caching assets like HTML, JavaScript, and CSS and storing data in indexeddb, service workers enable quick app startups, which is called warm boots, and usability even without an internet connection, enhancing user experience significantly. It is very important to understand the difference between browser's cache and Cache API. Browser's cache is controlled by the browser based on the cache control HTTP header. It is not very flexible. Manual reading or writing to this cache isn't possible, mainly aims to reduce network traffic for the user. Cache API is controlled by developers. It is not dependent on the cache control HTTP header. It's very flexible, allows manual data writing, and it's primarily used for offline accessibility and resource reusing. When the browser receives a response and it can be cached, there are two possible scenarios. The first one is when cache control is enabled. In this case, the file will be stored on disk in the browser's cache. The next time, the file will be retrieved from disk without a request to the server. This allows such files to be used offline and saves resources when the user is online. However, cache control settings should be carefully adjusted to avoid returning outdated content to the user. And the second scenario is when cache control is disabled. In this case, the browser has to make a request to the server. Currently, the usual scenario is to send a request to the CDN. If the file is relevant, the CDN will return a 304 status code and an empty body. This means that the browser can retrieve the resource from the local cache. In the second scenario, we have to do additional requests, but we decrease the risk of outdated files. IndexeddB is a NoSQL database available in browsers. It has large capacity, allows you to store large amounts of structured data. It is very powerful. It supports advanced features such as indexing, transactions, and versioning. It is fast because it supports asynchronous operations. It is available in web and service workers. The main problem with indexeddb is steeper learning curve. It's more difficult to develop and maintain. It is not recommended to use indexeddb SS. Wrappers like IDB can hide the complexity of indexeddb and make it much more convenient to use. IndexeDB is a very powerful tool, however it has a couple problems. The first one is intelligent tracking prevention. Safari's data, including local storage and indexeddb, is deleted after 7 days of inactivity. This means that we cannot consider the browser storage as a long-term storage of users' data. It can only be used as one-time cache. It doesn't work in private mode in Firefox. Also, we don't have an API to detect when a site is open in private mode and notify users of possible problems when using private mode. The only way is to try to open a connection with IDB and show a possible solution in case of failure. And quotas are confusing. Quotas vary from browser to browser. For example, in Firefox, the quota is shared among all subdomains. We can't create a predictable way to handle quota exceed errors that covers all browsers. Such problems are not unique to indexeddb. It's true. The problems with quotas and intelligent tracking prevention also affect other storages, for example, local and session storages. Why are we discussing this only now? The reason is that local and session storages are usually not used in scenarios where we use indexeddb. We typically use indexeddb in cases where we are relying on storage. We expect the data to be saved for a long period of time. Therefore, for indexeddb, such issues are very acute. Let's look at a few cases where indexeddb should be considered more than other storages. The first one is storing large amounts of data on the client side. With its high capacity and fast asynchronous API, indexeddb is a good choice for storing large amounts of data. Storing data with complex structure. IndexeDB supports almost all JavaScript types, except for some such as functions, for example. If we need to store such data, IndexeDB is a good choice. Storing binary files. IndexeDB supports binary file storage, which gives us many possibilities, such as storing media content for offline usage or uploading media files to the IndexeDB. And offline-first applications. Offline-first application must work as well offline as it does online. The other application simply has no backend and relies only on the client-side storages. Some storages share same quota. Quota is the disk space that the browser allocates for storing data. Following storages share same quota: local storage, indexeddb, cache API, WebSQL, and file system API. Another storages have individual quotas: cookies, session storage, and browser's cache. If one storage, for example indexeddb, consumes the entire shared quota, other storages that share the same quota, for example local storage, can't write data. This leads to the activation of the eviction policy, which we will discuss later. Shared quota includes local storage. Maximum capacity for local storage is from 5 to 10 megabytes, or the size of the shared quota. For cache API, maximum capacity is equal to the size of the shared quota, and for indexeddb, maximum capacity is equal to the size of the shared quota as well. Shared quota size for Chromium-based browsers is 60% of the total disk space for each origin. For Safari, it's 20% of the total disk space per origin, and for Firefox, it's 10% of total disk space per group. Group includes domain and subdomains, with a maximum of 10 GB in best effort mode. Individual quotas: for cookies it's 4 kilobytes, for session storage it's from 5 to 15 megabytes, and for browser cache it's controlled by the browser, so we shouldn't care about it. Even persistent storages can delete data. This is managed by the eviction policy. Browsers use one of two policies for eviction: best effort, which is used by default, and persistent mode. Best effort means that if the quota is exceeded, the browser will automatically remove data from the storage according to the least recently used policy. Persistent mode means that the browser will not automatically delete data from the storage. When the quota is exceeded, the write operations throws a quota exceeded error. When using persistent mode, it is important to wrap the write operation in a try-catch block. Persistent mode is needed when our application is highly dependent on offline storage, for example, if it is offline first. In Firefox, to switch a web application to persistent mode, we have to ask for user permissions. In Safari and Chromium-based browsers, allow or disallow switching to persistent mode happens automatically based on user's behavior. Databases, unlike client-side storages, reside on the server and form part of the backend architecture. However, we should consider them because sometimes it's smarter to just move data to the server. Let's look on advantages of remote databases. It is reliable. The database provides the highest reliability compared to the other storages we discussed earlier. It is secure. Storing sensitive data like personal information or credentials is safer on the server. It allows data sharing. Unlike client-side storage, databases facilitate data sharing across devices. Problems of databases includes complexity. Adding a database requires additional team resources or external resources, and high costs. Maintaining the database requires additional resources. Use cases. We can use it for sensitive data. Client-side storages is vulnerable to cross-site scripting attacks and other types of attacks. Sharing. Data that needs to be shared between devices should be stored in database. And important data. The database is the most reliable storage among others. In almost every web application, server-side databases are commonly used. They are secure, reliable, and don't face the same quota limitations as client-side storages. Why not use databases for all types of data? There are a couple reasons why we shouldn't do that. The first one is high costs. Databases includes various types of costs. This includes server disk space, handling user data requests, and scaling up infrastructure as user numbers grow, leading to a need for more servers. The next reason is slower interface. Every data interaction requires server requests. This can slow down the user interface, particularly for users with slower internet connection. And it's just impossible to use offline. Databases can be accessed offline. Without an internet connection, the application's functionality is significantly reduced, or application just becomes useless. The next thing we have to discuss is difference between storage and storage manager. The first thing we have to understand is that storage is not equal storage manager. Storage takes up physical space on the disks, provides an API for interactions, and has varying capacities and lifetimes. Persistent storage stores data forever until it will not be removed manually. Storage manager does not provide physical disk space. Store manager works on top of existing storage. Therefore, store manager can provide temporary or permanent storage. For example, Redux provides both options. It provides an interface for working with storage and facilitates data operations, such as create, read, update, delete operations, subscriptions for updates, and others. We have discussed all the theoretical material. Now let's look at a real-life example. We will take a Facebook as an example. It is a very popular question in a system design interviews. Therefore, discussing such a topic can be very useful. Let's take a look at the elements that make up Facebook. The first one is search. Users can search for other users and, for example, groups. Search can also include various filters and sorting options. The next feature is adding posts. Users can add new posts with title, tags, and attachments. Users' data includes all information related to the user, for example, friends list, groups, etc. It's not about the design of the real Facebook. Imagine you have never seen the real Facebook and have no idea how it works. During the interview, we only work with functional requirements and our knowledge. Before we start, let's try to understand how to make the decision. We have omitted the URL, cookies, and cache because these storages are used in very specific cases. We can choose the appropriate storage depending on the lifetime and importance of the data. For short-lived and not very important data, we can choose session storage. For long-lived data, we should prefer a database because any client-side storage is not very reliable. The exception is offline applications that are used only or mostly offline, in which case we should use an indexeddb even for long-lived and important data. Another exception is sensitive data such as passwords, tokens, etc. We mustn't store it on the client side because they are vulnerable to cross-site scripting attacks. We should always choose storage based on the actual requirements of the application, and this graphic is just a hint that can help you to make the choice. Let's start with search. Users can search for other users by name, city, age, and other parameters. We can also sort search results by date, popularity, and more. What type of storage can we use for these data? Search parameters are not very important data. Loss of such data is not a big problem. Search parameters are short-lived data. It is quite possible that we may want to save the configuration of such filters in our browser bookmarks or share with friends. That's why URL search parameters are a good choice. When a user creates a new post, it is saved in the database. Creating a post may take some time. Users may want to create a draft and come back to it later. We also need to decide where to store such drafts. We have three possible locations. The first one is local storage, the simplest solution, suitable when we don't need to store many drafts and when the draft is a plain text. The next option is indexeddb. It's more complex to maintain but gives us more scalability. It's suitable for a large number of drafts, perhaps with a more complex structure, which includes title, content, tags, and attachments. And the last option is database, the most robust solution. Also allows data sharing between devices. It covers all possible cases, but has disadvantages. Difficult to maintain and requires requests to the server to read and write data. The final choice is based on the functional requirements of the application. A database is the best solution in terms of reliability. It also allows users to start writing a post on one device and continue on another the next time. However, it might not be needed if we expect that the post will be relatively short and will be completed within a few sessions on one device. If we choose indexeddb or local storage to store drafts, it won't be the most convenient or reliable solutions, but we can do it relatively quickly because we don't need to involve the backend team in the development. If we decide that we need all the features and we have the time and resources to develop, I recommend to use a remote database with indexeddb for offline mode only. Why not local storage? Local storage is good for simple data. In our case, we're dealing with a complex structure. A post may have a title, text, and other fields. Posts can be long, and since the local storage API is synchronous, reading and writing such large amounts of data can slow down the application. And finally, local storage does not support binary files, which can be useful offline if users want to add media files to a post. Why not indexeddb? We will use indexeddb as an additional storage when the user is offline. However, we will use a remote database as our primary storage. Why? Because indexeddb does not fulfill two criteria that might be important for drafts. Indexeddb does not allow data sharing between devices, and indexeddb is not completely reliable. Data loss is still very likely. Therefore, we will use a remote database as our primary storage. Let's look at the big picture. The first scenario is that the user is online. In this case, we simply save the drafts to the remote database. Second scenario, when the user is offline. In this case, we save the drafts to the indexeddb. And the last scenario is when the user comes back online. In this case, we have to synchronize the indexeddb and remote-db. Let's summarize everything we have learned. The first one is cookies, use cases, session management, tracking, personalization. Key advantages: secure, sent to the server automatically. Key disadvantages: small capacity increases HTTP overhead. URL search parameters. Use cases, page state. K advantages, sharing. K disadvantages, small capacity increases URL length. Local storage. Use cases, storing long-term data. K advantages, simplicity. K disadvantages, slow API, small capacity, and limited features. Session storage. Use cases, global data. K advantages, automatic eviction policy. K disadvantages, inherited from local storage. Indexeddb. Use cases, storing long-term data and offline usage. K advantages, big capacity, powerful, fast asynchronous API. K disadvantages, stepper learning curve, require wrappers to hide the complexity. And remote database. Use cases, storing long-term or sensitive data. K advantages, secure and reliable. And K disadvantages, it's expensive.
That's all for today. If you found this video useful, please don't forget to click the like button and subscribe to the channel. Stay tuned for more upcoming videos soon. See you next time. Bye.